Hello, my lovely students. So, we are in our last chapter. Chapter 6 is on exponential and logarithmic functions. We have a whole lot of material shoved into this 1 week, but all of it is a review, except for one formula that I'm not even sure we'll see like on the final. So, we're not going to focus on log properties. That's actually going to be section 6.3 next week. But we got a whole lot of other stuff. So I'm going to try to go through it as quick as I can. So let's begin. So exponential growth is an increase based on a constant multiplicative rate. So we are not adding the same rate every time. We're multiplying by the same rate every time. So it gets bigger much faster. So here we've got g of x 2 times x. We just add 2 every time, even though the function itself is multiplication. 2 to the x, the change between each function value is times 2. All right, so exponential growth is the same percentage change over equal increments of, usually it's time, or whatever the domain is. Linear growth is the same amount. We're adding the same instead of multiplying by the same. All right, here we have the exponential function with the graph. This is 2 to the x. Later, we're going to talk about function transformations on this. But exponentials, unless they're shifted, do not touch the x-axis. So that makes y equals 0 the horizontal asymptote. An unshifted, unstretched graph has a y-intercept at 1 because anything to the 0 power is 1, except for 0. We don't talk about 0 to the 0 power. All right, so we have here some functions which are not exponential. Okay, so exponential functions, let me rewind just a little bit. A is a non-zero real number. So the number not being raised to the power but multiplied out front can be positive or negative. If it was 0, we just get a very boring flat line. B is any positive real number. So B can't be negative, B can't be 0, and we have another qualification that B can't be 1, but only because 1 is another boring flat line. So when we're looking at our exponentials here, it's, do we have number raised to a power, and is the number non-negative and not 0? All right, so G here, not exponential, and J here, not exponential because it's a -2. Now, if there weren't parentheses around it, ironically, it would be exponential. But basically, you can think of it like negative numbers raised to powers. Like if I square it, it's positive, but if I cube it, it's negative. So like, what would the graph look like? It makes no sense. The 4 to the 3 times x minus 2, like it's got some shifting and stretching going on in there, but it is a number raised to an x-type power, so it is exponential. And then the 1/3 to the x, we can have fractions in there as long as they're positive. And now evaluating without using a calculator, or use your calculator, I don't care. So f of 2. All right, so let's start with our f of x. 5 times 3 to the thing plus 1. And our thing here instead of the x is 2. All right, so I have 5 times 3. 2 plus 1 is 3. So anytime we have an exponent, like the whole exponent is considered its own set of parentheses. Until it's down to a single number, you have to use other things to simplify it. So now I have a base raised to a power, exponent next, so 3 to the third is 27. Then 5 times 27, 5 times 20 is 100, 5 times 7 is 35, so 135. So I did it without a calculator, do it with math, it doesn't matter. The whole point was more to see the steps, being able to look at a function and break down what happens first, what happens next. That is a skill you will need. All right, so exponential growth and exponential decay. This is where we bring up this phrasing of growth factor versus growth rate. But the catch is these two words are not used consistently outside of this class. So you always have to read these kind of questions with a grain of salt. But for ours, if we say what is the growth rate, and we're talking about an exponential growth, then our b value is 1 plus r. So r is b minus 1. And then if it's a decay graph, which happens when b is between 0 and 1, growth, the b value, which is the thing we see in the function. If it's bigger than 1, the thing grows. If it's between 0 and 1, if it's a fraction, but a lot of times it'll be written as a decimal, then it's decay. But the decay rate is going to be 1 minus b. If you do b minus 1, you'll get the decay rate, but negative, which to me indicates it's a decay, but they don't want you to put negative rates, so yeah. So 2 formulas instead of 1. All right, so we have here that we have the population of India has a growth rate of 1.2%, and the population was about 1.25 billion in the year 2013. So since it's a growth rate, we can use an exponential function to model it. The b value will be 1 plus the growth rate as a decimal. So that's why we have 1 plus, like 1.012, because that's 1 plus 0.012. So then it says, to the nearest thousandth, what will the population of India be in 2031? So to answer this question, we first have to understand, where does it start? So T is the number of years since 2013. So when we're asking what's the population in 2031, we need to know how many years is 2031 from 2013, which we figure out by subtracting. So it looks like 18 years. Since 2013. So 18 is our T value. And then it says to the nearest thousandth. So now we have P of T equals 1.25, that initial population. Remember though, that initial population was in billions. So our answer here will be in billions. It'll match the unit of our initial value. Then the 1.012. And this is where we put our 18. And then this is where we use the calculator. No one expects you to try to crunch 1.012 to the 18th by hand. That's ridiculous. All right, so let's see what we get here. 1.25 times 1.012 to the 18, close. All right. 1.54938, blah, 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 blah. So thousandth, 10th, 100,000. So our answer is 1.549 billion. I know web work doesn't make you write units, but anytime you do a word problem, you should always ask yourself, what is the units on this? What does this number mean? So in this case, this is saying in the year 2031, we would expect India to have a population of about 1.549 billion. Then we have a much longer problem. So we have a barbecue opened downtown right before inflation peaked. So the barbecue sales at the restaurant are represented by this function here, A of t. And each year t, so t is in years. With the amount of meat sold in thousands of pounds, and t being the number of years since 2021. So is it growth, decay, or neither? So 103 would be our initial value. When t is 0, that is what we would get. So that is the thousands of pounds of meat sold the first year. But the 0.955, that's less than 1. So this indicates that this is going to be exponential decay. So because 0.955 is less than 1, it's decay. So the initial is 103, but how can you tell algebraically? So initial value comes from zeros. So A of 0 would be 103 times 0.955 to the 0. A number raised to the 0 power is 1. 103 times 1 is 103. So 103,000 LBS is pounds of meat. And then it says, what is the rate for the function? So that is not the factor, which is our B value. This is the decay rate, since this is a decay graph. All right. So since, remember, decay rates are always 1 unit off from our B value. So if I did our B value minus 1, I would get a negative number. So we flip it over. I'm going to do 1 minus 0.955, which gives us the decimal of 0.045, which we can convert to a percentage. So that is 4.5% decay. And then it asks, if inflation continues at its current levels, how many pounds of barbecue can Pinkertons expect to sell in 2026? Round your answer to the nearest pound. I'm going to highlight that because that is like a trick question. Because the nearest pound is not the nearest whole number, it'll be the nearest thousandth because the function gives us thousands of pounds. So 2026 is 5 years from 2021. So this is asking us to find A of 5. So we have 103 times 0.955 to the fifth. And this is because 2026 minus 2021 is 5. All right, let's crunch that number up. 103 times 0.955 to the 5. All right, A of 5 is 81.818984, blah, blah, blah. So to the nearest pound, remember this is thousands of pounds. So if I want to know in pounds, I would have to multiply this by 1,000. Which really just moves the decimal 3 places over. So this would be 81,800 and it's going to round up to 19 pounds of meat. Now, if they ask that on web work, they should take 81,819, but I could see them wanting 81.819 just because web work can be annoying. All right, we're going to call it on this one. Then we're going to have some algebraic ugliness of find the function given some points.